reinforcement learning. Happy Halloween also, great. Yeah. So the first part of the lecture, you can use the PDF from last time, all right? You remember we didn't complete it. By the time we reach at the end, Josh will have updated the website. Our topic today is AlphaZero, AlphaGo Zero, and the next topic that we'll visit once this is done is model-based reinforcement learning from sensory input, directly from videos. If you remember, where we ended last time is we described the complicated process where, actually, let me remind you the 4 steps here. There are this 1, 2, 3, 4 steps where we train policies and value functions, right, from imitating human experts and through self-play, reinforcement learning, and then we use those policy networks and value networks during Monte Carlo research at test time. Do you guys remember that? Okay. And if you remember, we had 2 policy networks. One we call the cheap one that we used outside the tree, because outside the tree, we really need to call the policy network many, many times. Why that policy network is to be cheap? I mean, a more expensive one would always do better. You agree? Why would somebody take that compromise and, make the network smaller, train it on the same amount of data, right, but have worse performance? What was the motivation that we gave there? Yes. Yeah, why we want faster rollouts? In a fixed amount of time, right? Yes, exactly. Because, we have a timer, right? So we don't have infinite thinking time. Yeah, exactly. And to be honest, that process, apart from being super complex, if you remember how we described it, it's also this non-satisfying thing that what you train and what you test is completely different, right? So we train that value networks and reinforcement and those policies in a different way that we use them at test time. Of course, the better our policies, the better our Monte Carlo research would be guided, but ideally we want something uniform that we train and test in the same way, okay? But do you have any questions from the AlphaGo? From the AlphaGo paper? Yes. So who had the opportunity to read the paper? Great. So what did you guys think? It's a huge a landmark in, let's say, self-learning agents or reinforcement learning agents and so on. Do you see it was the first time that we had a planning procedure be coupled with a learning network? Okay. Any questions, any comments on whatever you read from last time, guys? That's fine. Yes, please.
I thought it was cool how the guys know like one game.
Yeah, but and also it's not clear what happened. It's not clear if the board configuration was not well registered. So it's like this super weird engineering problem or something else, right? And I also, another thing that I really liked is when you see the algorithm seeing that its values are getting lower and lower, that you really feel like, oh, it really knows it's going to lose, because you can estimate your value functions, like you feel the pain because it's aware. It knows the value function is going lower, but doesn't know what to do to fix it up. So I thought that was interesting. But yeah, so now today is a major, even bigger, let's say, maybe less advertised, but I would say even more major breakthrough we're going to visit today, guys. It's so subtle. Many people don't get it. People still try to figure this out in papers. And here is how I would like to, present this to you guys. So this is the next paper coming from this lab. Yeah. So AlphaGo was the first. AlphaGo Zero was the next. AlphaZero was the generalization of the AlphaGo Zero algorithm to other games. All right. Mu Zero is what we're going to visit at probably on Wednesday, which is the same things, but with a learned model. Actually, let me ask you this question. In previous lecture, when we discussed about AlphaGo and Monte Carlo research, you had to use a model there to do these look-aheads. This model was learned or no? No. Does anybody think that this model was learned? Okay, so it's not learned. And whatever I'm going to discuss now, again, the model is not learned. Okay, only in mu zero, the model is learned. Okay, just to be clear. Now, what is the major idea here? So here's the major idea. So far, we were using look-ahead search at online planning at test time. Correct? There was no planning. There was no Monte Carlo research at training time. Do you all agree with this? Okay. So, and before in this series of lectures, we've seen Monte Carlo research to be useful at training time. I'm not sure if you remember, but we had used it a long time away when we talked about DQ networks. And we said, instead of having our DQN model free learner, we may have a Monte Carlo research planner with a known model to come up with states paired with actions, all right, or states paired with Q values. You remember we had these alternatives. So either you're going to train a regressor for the Q or a classifier for the policy. So we saw that this was very useful, right? That's we use the planner to train, right? To discover those good actions, to pair states and actions, and then use this pairing to learn how to act, correct? So here, now the natural question is, can we use this here? Why don't we use this planning process at training time? And AlphaGo Zero does exactly that. It uses Monte Carlo research at training time. Okay, this is the main idea here. The Monte Carlo research, we'll see how to use it at training time. And I'll tell you what this means. And as a result, you come up with an amazing self-learning method, okay, amazing planner that you really don't need any work start from human experts anymore. You can start from scratch. So this is major, okay? So here we have a self-learning agent that learns by mental planning. So basically what means is that you sit there and think through and you plan through. And so basically the Monte Carlo research is called the thinking time. So before acting, whatever we've seen so far that our exploration was super dumb, right? You have a policy, you add some exploration noise, you just act. Here, this exploration is going to be extremely deliberate. We'll be thinking and thinking and thinking at every step. So our training agents, our agents during training, will take much longer to act in the world because they're going to think longer. However, the result of the thinking process will be so good that with much less experience is going to result to much better policies. Okay, now why this is super major? Because even if you go to Atari games, which Atari games, I'm not sure, I think we all agree that you don't need to plan. First of all, you don't have time to plan because you need to be super fast and reactive when you play. But even there, we're going to see an amazing paper that says planning is useful at training time. At test time, you don't need to plan for Atari. You just deploy your policy reactively. But to come up with a policy, to train that policy, is very useful to go through planning because you just end up with a much better search process. Is that clear? So that's why. So this is very, very general. Yeah, this is very general. Is that okay? Do you see the implications here? Okay. Yeah, so this is really, really important. So let's see the details. So now the other amazing thing in that paper is the simplicity of this process. Now, despite the fact that the algorithm is simple, it may be difficult to grasp. So now we need to be a little bit careful here. So what are we going to do is the following. We're still going to have a policy network with some parameters theta, and we're still going to have a value network. Okay, so this don't change. However, what are we going to be doing at training time is we're going to be using these current policy and value networks to guide the Monte Carlo research process in a similar fashion that we guided the Monte Carlo research process at the test time of AlphaGo. Okay. Now you need to understand that although in AlphaGo at test time, the value networks and policies were awesome because you had pre-trained them, here in the beginning, they're going to be random. All right. Because you will initialize those policies and value randomly. Okay. However, despite the fact that they're random, okay, through look ahead with this awesome, Monte Carlo research planning process, you will come up with action estimates that are better. And then you will imitate those. So you will do exactly what we did a long time ago. We will just be imitating the results of the planning process. And then we'll go back and plan again with a better policy and a better value function. And we'll iterate between updating our policy and value networks, feeding them in the planning process and getting better ideas of what actions to imitate, imitating them again, plan again, and so on. That's how it's going to work. So you can think about this Monte Carlo tree search process as a policy improvement operator. You start with some policy value network, you feed them in the planning process, better action estimates come out and value estimates. Then you imitate those, and again, you start, you plan, you get some improvement, and then you iterate. All right? All right, so we'll go now into the details. So that was the big picture. So first of all, let me discuss about that, how that Monte Carlo tree search process with the value and policy network will look like. This is very similar to our Wednesday's lecture. It's similar, almost the same. It's almost the same. So however, it's simplified, and let me tell you, there are some very important simplifications, which are the following. This guy is exactly the same as on Wednesday. So our action selection inside the tree will combine the current Q estimate and our policy prior, P theta, and, you know, all these exploration bonuses here and so on. So this is exactly what we said on Wednesday. Do you remember that, guys? Do you remember where this formula came up? Does anybody want to comment about this formula? How did we come up with it? Like where we started, where Monte Carlo research does, and how we updated it? Yes?
Monte Carlo research usually uses the UCB exploration.
Right. So if you remove that policy, the whatever remains is like a UCB type of exploration, right? A combination of exploration bonus and some exploitation Q value, right? With some weight in between. So here we have UCB plus prior policy, correct? Okay. So this is the same as Wednesday. This is the prior, and that's why you have Q plus U, the exploration bonus, sure. That prior, yeah, is the policy. Here is the prior. When a leaf is node, yes, we compute its prior probability, we feed it into the policy and the value, and we save those. This is exactly what we said. Here is the tiny little change, and it's actually a beautiful change because it makes things much simpler. So now you can forget about cheap rollout policy. So we're going to be doing nothing outside the tree. Super simple, right? So the only thing we'll be doing is once we reach our frontier node, we're going to feed that node into our value network. We'll get a number. That number is going to be V. And that's it. That's all. There's not going to be any rollout and some weighted combination between that V and the reward we get and so on. None of this. Amazing, right? So basically our value network will just evaluate for us the leaf nodes and where these evaluations are used. Does anybody remember where those V's are used? Why we evaluate the leaf nodes? What do we do with them? Yes. Yeah, exactly. So the Q things that you saw in the previous thing, this Q is exactly propagation of the V's of the leaf nodes. Essentially, you just copy that V in all earlier leaves and count. You just count how many V's I got. Let's sum the V's, divide by how many times I've been in that, action, and that's your Q. All right. So this is a major simplification here of how we evaluate the leaf nodes. Is any question on how we evaluate the leaf nodes? Okay, so since there are no questions, does anybody want to tell us on Wednesday how we evaluated the leaf nodes? Yes?
We did one full rollout and then combined the value with what our value network thinks, plus did we win this trial or not as a weighted sum of those two values.
Yes, I see. I agree.
We ignored our value network here.
No, we ignore the random rollout here. There's no rollout. Okay, nobody's going to try to play from that leaf node till the end of the game. All right? We're just going to fit the leaf into our... Do you see? So do you agree with what our colleague said? I also think we had some weighted sum. Now that, and this is a major improvement because that was extremely expensive to try to play all the time till the end of the game. That's super expensive just to get an extremely super noisy idea of your reward. Can you imagine how extremely noisy that the reward would have been? Okay, so we got rid of this. Yeah, And that's it. So we're going to do 1,600 rollouts. So if you start from scratch and you do 1,600 rollouts, how many nodes you have in your tree? Yeah.
One for each roll.
Yeah, 1,600. Because so I'll show you some visual picturing of that. But yes, the way MCTS it works is that at every rollout, you know, add one extra, state, right? Yeah, and now here is the most important thing. Okay, let's assume we did our Monte Carlo tree search. We did multiple threads. We made our network, our tree, sorry. And then what happens? Then what do we do at the root? Does anybody remember what we did at the root on Wednesday? How did we play? Right? We were there, and Lisa Doll is watching, and we need to play an action. Yes?
Most frequent action.
Yes, so the most frequent, this is what we did. So today, what we're going to do is we're going to take the distribution of actions at the root, which means how many times we played each one, and we're going to use this as a target for our policy. Essentially, we'll, train with a soft cross-entropy loss to say, oh, yeah, action 1 should be used 0.1% of the time, and action 2 should be used 0.3% of the time, and then, okay, that's how we're going to do it. So let's see. So let's assume our simulation budget is 4. So we start with the root, and then here is the first trajectory. We added this extra state. Here is the second trajectory, and our second rollout. Here is our third, and here is our fourth rollout. And we made a tree, and that tree has 4 nodes, all right? And the end tells you how many times you've visited a particular state, correct? And this is how you were selecting the actions within your tree. And outside of the tree, nobody cares anymore because we just use our value network to evaluate. And, yeah, okay. So, and then at the end of your budget, you go to the root, you look at the visit distribution, how many times you played each action with the total number of rollouts, all right? And then you train your policy network to imitate that visitation distribution. That's how you train your policy, okay? You imitate the planner. And because here our policies are not deterministic, they're probability distribution, you try to imitate the probability distribution. So this is just supervised learning here, right? So is that clear? Okay, this is very simple. It's as if you have a categorical distribution. Let's say you have 30 actions. I mean, okay, in Go, you're going to have hundreds. And instead of saying 1 versus 0, you have a soft distribution. You say, okay, action 190 was used 70% of the time, and so on. And you try to match that soft distribution. That, very simple. All right? Yes. Any questions here? Yes?
Can we go back to the simplification?
Sure. Yeah, let's go to the simplification. We're not done yet, by the way, but yes. So let's go to the simplification. Here it is.
So this B of SL is what our value network means about this.
Yes. Yes. So every internal node, I'm an internal node, and let's say for me, 30 rollouts have passed, and each of those 30 rollouts resulted in 30 different leaf nodes. And each one of those leaf nodes has a value, and my Q is going to be the sum of those values divided by 30, right? Like just counting. We just do counting to estimate the Qs. Okay, so we're almost there. Let's see. So we went through that. So this is how it works now. So yes, please. Very good question. Yeah, so here we have discrete. There has been some extensions very recently in some very recent ICML, maybe last year. We can visit those. I haven't added them in the course, but yes, there are. But maybe I can put it so whoever is interested can go and check. Okay? Yes?
Do you think you're close to a terminal node? Is it worth it to do a rollout, or is that still too noisy? If you have some heuristic to say, I'm 3 steps from the terminal position.
Right, but the thing is that the closer you are to a terminal, the more informed your value network is going to be, right? While earlier in the game, the value will say, oh, who knows who's going to win? I mean, later in the game, also in chess, right? When you're very close, I mean, you can say, yes, I know that in 3 moves, this guy's going to win, let's say. Do you see? So there's no reason to a rollout to be more informative than the value function towards the end of the game.
Got it. Okay, thank you.
Mhm. Other questions? Yeah.
How much is it relevant, the problem that we were talking about before of trying to imitate the planner and then going off of the problems that we were talking about with imitating a planner, and how if we went off of what the planner planned, then we're kind of in uncharted territory. Is that relevant?
Oh, I see. Yeah, great. So your colleague is saying we had discussed earlier in the course how there is this planner, and that planner, by the way, was super disjoint to the policy we're training, right? So the policy were no way entering there, just collecting some data. And we had this problem of that we had to solve with interleaving, where, the planner suggests some set of actions, and then we use the policy to imitate those actions, but then we deploy the policy, and the policy lands in states that actually the planner hasn't seen. And now we need to recollect those data, ask again, query the planner again for ground truth actions there, and then we imitate and we iterate, correct? Now you don't have this problem anymore, because during training, let me think, whatever is going to come out of this learning process, you're just going to directly use it again. Do you see? So let's finish the slide to see how this whole learning process, and then we'll see. Great question. Yeah. So just following up on what your colleague said, let's see. So now everything works in a very tight loop together. Let me tell you, you initialize your value and policy networks. These are just the weights of your neural network. And then you self-play, means that you play against yourself. All right. So you use your own policies and value functions in Monte Carlo research to select actions both for yourself and for the opponent. So you wake up in the beginning of Go, let's say everybody is at the same as 0, because the same with chess, I think they always start from the same configuration. And let's say this is the S1 here. And then you need to act. And how you're going to act? Because to play, you need to just deploy some policy, right? You need to start acting. You're not going to be sampling actions from your policy. Where are you going to be sampling actions from? Yes?
The NGTS at visitation distribution.
Yeah, from, let's say, the action distribution that the planner suggests to you. Okay, but that planner has your policy inside. We have we just saw how that planner uses your policy and value function to plan, correct? So here, you take your visitation distribution. Okay, so this is distribution. So what do you do with distribution in order to plan? You just sample from it. You're like, okay, action 193. You act. Here is alpha. This tilde means you sample from that visitation distribution. Okay. Then now the state changes. Again, you think. You get another distribution. You sample from it, and so on. Next state again MCTS. Again the visitation distribution. You sample from it, and so on. Of course, the trees, you can carry them from state to state. Do you see? You don't need to start your tree from scratch. We have seen this before, right? You take the subtree and you root there. So that's great. But can you imagine how much time this takes? A very long time. Because to complete the whole game, you have so many planning processes. But in any case, at some point, somebody is going to win or lose. Okay, the one going to win, the other is going to lose. And you get this final reward Z, which is going to be 1 or -1. And here is what you're going to do. So this, actually, you do that not once. You play multiple games. And then what you do is now you go and update your network. How you update your network? Well, for each of the states that you visited, of course, during the games that you played, you supervise there your value and action network. How? You ask it to imitate the visitation distribution. And so this is standard soft cross entropy loss. And you ask the value network to spit out these rewards, and this is standard regression. That's it. Yeah, and here it says that you spend 0.4 seconds thinking time per move. So this is a very slow game because your Monte Carlo research is expensive. Of course, this depends on your resources. And despite that, this method requires much less GPUs to play than, let's say, AlphaGo, okay? Because it lands in much better actions. And I'm not sure if you noticed, but there is no bootstrapping from human expert moves here. You don't start from there. You don't warm start yourself. Okay, so basically this is the training process, guys. You initialize your policy and value networks. You go and play against yourself, and your actions are sampled from the planner, modulated by your action and value networks. And then you update your networks, and you go back, and then update, and then you go back, and then update, and you iterate. And I don't think that they play one game and then update. I think you play multiple games and then update. And now you may say, okay, what is the interleaving? How many games you need to play and then update? I mean, I think this is a hyperparameter. But it's a good question, but it's a hyperparameter. Okay. So as you see, here the planner is totally in sync with the policy. And there is no such thing as distribution mismatch here because there's no mismatch. Whatever you told me, I go again and apply it, and I see the new values and update myself and so on. Everything is in time loop. And my question is for you, the following. At test time, what are you going to do? Because so far we've been training. Is that clear that that was the training? Okay. So what is going to happen at test time? Which policy? So what are the options that we have at test time? Who would like to tell us what are the options? Yes.
You could either just sample directly from the policy that we learned, or use it in the value function to inform MCTS like we did in training.
Exactly the same way we did in training, right? Great. So now let's all discuss. First of all, are these two options clear to everybody? That's number one important thing that we need to. Do you see that we have two options? Either we will directly sample from our policy reactively, or at this time also we're going to plan. Okay? All right, great. So now let's all discuss what do you think are the pros and cons on each one, and do we think that planning is important at test time? Yes.
It seems like the only case in which you do it first is if you didn't really have time to do MCTS, like we're saying, you don't have the entirety. But like the second, if we have time, it will give us like better results. And so like in like a game like this, like a 0.4 seconds for moves is very reasonable. So we're better to do MCTS is gonna go a little bit better. Like results in the cost a little bit more time, but you have that to spare because you're not like required to move like immediately.
Excellent. Yes. So Max said the following. He said, okay, great. We have two options. When I have time, I'm going to plan. If I don't have time, I'm not going to plan. Right? And if I plan, I will always land to better actions. Other ideas? Yes.
I'm not totally sure that planning will give us better actions here. That's not entirely obvious to me because the neural network is trained to mimic the planning distribution very closely. They train it for long enough, which I believe they must have to be
Sure.
chess masters. Yeah, I'm not very sure if there's any advantage to planning.
Excellent. So now our other colleague says, I just don't see why I need to plan since I distill the results of the planner into my policy network. Okay, very, very, very logical concern. Other ideas? What you guys think? Yes.
The policy after an amount of time should approximate planning, but until then, it will always be slightly off.
Excellent. So now your other colleague says, well, if you train enough under an infinite number of samples, yes, the policy should be identical. That's exactly what Sid Srinivasa, like the Amazon robotics director, said to me as an answer. He said, planning should help under infinite amount of data. Yeah, sure, you can be reactive about everything, right? I mean, if you spend your life bartendering, right, you don't need to plan. You just, do you see? Exactly. And if you spend, it's as if you spend multiple lives doing everything infinite amount of times under infinite, yes, then you don't need to plan. By the way, this is absolutely important question. We're going to see an amazing paper because there is this confusion about people how planning helps. And people think that, planning helps me to generalize, which is completely crazy because all the planning, how good the planning is depends on your representation function, your dynamics. So if your dynamics doesn't generalize, forget about the planning trying to help you out anywhere. And they show in that paper, the paper is called The Role of Planning in Reinforcement Learning, that for Atari and all other games, all these other suits, Atari, it doesn't help. It doesn't help you to plan at test time. The policy indeed has learned everything. It's very helpful at training time to discover the right actions. But for strategic games like Go, now I'm going to show you what happens, which also agrees with the paper. Here is the row network. 1 second. So this is alpha goes 0. Yes. So look ahead tremendously improve over the basic policy. The row network is whatever you're saying here is this pi theta that we used to guide the search. So this is our policy. This is the policy when you endow it into the planning procedure. Much, much better performance in these strategic domains. Okay. And yes. So now the question would have been, oh, what if we just, make the capacity of the network 10 times larger, right? And then feed also 10 times more data. And let's see the trend. If the trend starts closing, then we know that your hypothesis is correct. So that's sure. Under infinite data and enormous capacity of networks, we should be able to emulate reactively the solution to every board configuration. And indeed, chess masters, the first 30 moves, they don't think a lot. They just reactively, execute. But then at some point, they start thinking. Okay. Is that clear? Yes.
I imagine no matter also how much training data you have and compute, there's also going to be some loss by a finite network that approximates a possibly complex function.
Yeah, I mean, Go is also not infinite. Nothing is infinite. You know what Einstein said, right? There's only one thing that is infinite, human stupidity. So that's the only thing that is infinite. But other than that, yeah, but I see your point. I think it is a very interesting thing to check. Other questions? Yes.
What do we mean by look ahead tremendously improves? Not rolling out till the end.
But well, yes, it doesn't mean. So look ahead. By the way, just to be clear, look ahead. Most of the times we will never go till the end. In fact, I'm going to show you an amazing paper towards the end of today's lecture. We're never going to plan towards the end. It doesn't matter. We just need to plan ahead and then apply our value functions not to our current state, but rather to unroll future state. This is look ahead. Okay. So just the Monte Carlo research planner endowed with that policy does much better. All right.
So this would be like an hyperparameter, right? How much do I want to do given this much budget time?
Yes, although I need to tell you, the finding is the longer you look, the better. But great question, though. Yes. Let me tell you, here where the models are perfect, accurate, like you don't learn, the more you look ahead, the better you do. You can look ahead more at just time than what you trained on, and still you're going to be doing better. Okay? Now, once you start learning models, you will see that at some point, the end errors will be compounding, and it's not going to be helpful to look ahead further. Okay? Other questions? Yes.
So when we're training our policy network based on the visitations of the planner.
Yeah.
But when we're deploying and we're still using the planner, are we
still looking at the visitation?
Still using that visitation.
But in sample from. No, you can take argmax. Yes, you take argmax. Absolutely. That's the natural thing to do.
Okay.
That's also what we did for actor critic, right? We just took the argmax at this time while we had the soft distribution of our actions at training time.
And you'd want to do that unless there was an advantage to acting somewhat randomly.
Which usually doesn't, but yes. In these games of full, it doesn't in these games, right? Yeah. So argmax is totally okay, right? And also all these domains, guys, are deterministic. Just to be clear, these are deterministic dynamics. There is no stochasticity. And the models that we're going to learn for these domains are also deterministic models. But we'll also visit papers that learn stochastic models, like, for example, Atari is stochastic. Okay? Yeah, so that's all what I wanted to show you. Here is the last slide, which is, again, something obvious. So RL versus supervised learning. Of course, if you do reinforcement learning, you do worse on imitating human experts, but you do better at winning the game. And if you do supervised learning, you do better at imitating human experts, but you do worse on winning the game. For example, so here, MSc of professional game outcomes. So here this estimated better, but prediction accuracy on professional moves, as you see, the supervised learning does better than reinforcement learning. But on ELO rating, which is the average rewards, the reinforcement learning does better. You see that at some point, although the supervised starts higher because it has a warm start, eventually the RL that we discussed today, which is all the way reinforcement learning, right? There is no human input whatsoever. eventually wins. Correct? Okay, so this is the first thing we had to cover today. Now we're going to go back to some also very important topic, which is as follows. I mean, our AI agents, right? Artificial agents need to be able to handle real sensory input. And by the way, this is a big discussion. By putting us all the time as, let's say, AI goals and AI landmarks, who can do well in poker, who can do well in Go, and so on, then you take the sensory representation problem out of your question. But the truth is the following: humans, and do not take educated humans, just take, the majority of humans in the planet. They also, many of them don't even need to know how to read and write, right? Let alone play Go, okay? But they can still move, and they're very effective, and they adapt. And in the different environments, floods, heat, and so on, they can still walk, they can still pick up things, and so on. So where humans excel is this sensory motor control. All right, this is where humans excel. I'm not sure if you guys understand that or you agree also. But basically, let's say, I don't know if Minsky had said that, we mentioned this in lecture 1. He said always AI thought to be what male white scientists could achieve, let's say in 1980s and so on. But you know what? This may not be, the diamond of what evolution produced. What evolution produced is super competent sensory motor learners, super adaptive, right? So if we want to talk about AI, just going to those idealized domains are still extremely interesting, and still the solutions will probably and will surely solve incredible problems. And I'm not sure if you read actually this amazing recent paper of they used a similar method like what we just discussed today, AlphaZero, to plan how to do matrix multiplication faster. Okay, so this is fantastic because now you can just fire the mathematicians. You can just have learners but it is true. It is true, and we'll see this again and again. You don't need to have people thinking through. You just need to learn and plan and see which ones actually lands in smaller computation. Which sequence of action will add this smaller computation? Of course, you need domain knowledge to design these learning methods, but you predominantly also need how methods that can actually learn by trying things out, whatever we discussed today. So I think the tremendous benefit of the algorithm we just visited is its applicability to a wide range of domains. For example, drug discovery sounds impossible because you need to be able to do a lot of simulations, by the way, which in drug discovery, it's impossible because you need to try every drug. So I don't think this falls under this umbrella, but optimizing, algorithms or, mathematical formulas and so on, it turns out that this was possible. You know which paper I'm talking about, right? A very famous, alpha tensor. So this alpha comes from here. Oh, okay. So I would check, or at least I read the introduction and so on to see this huge impact. And we're talking about a huge amount of revenue coming out of just shrinking and making those computations faster, because matrix multiplication is used everywhere. Okay, great. Well, now we're going to go back to our kind of sensory grounded agents, which is fine. Okay, I think it might be confusing to switch between these two worlds. Because in one world, what is, I think here is the confusing part. In one world, in the idealized world, the person that wins is the person that can think through and roll a lot of trajectories and plan and be able to manage his search, the breadth and the depth of its search well. Now, in the sensory grounded world, the person that will win is the person that can generalize across domains. So the person that will have the better representations, but the person is the agent, okay? So the agent that will have the best representations, that is able to match, this cuboid to a much wider cuboid, this bottle to a different bottle, this is the person that's going to win, not the person that's going to be thinking through and unrolling trajectories. Is that clear? So unfortunately there is this disconnect, but that's fine. So we will see a lot of papers, you'll see how the different things play out, etc. So today's lecture, just to be clear, is not about generalization. We're gonna still, focus on discovery. So let me say it one more time. There is a huge chunk of the literature that is focused on, I give you a bunch of environments, discover the solution, solve those environments. And there is another huge chunk of literature, which is the representation learning literature, that doesn't care about discovery, just cares about imitation. Okay, and how do you give me the solutions, and I'll be able to, transfer those to new domains. So this is the reinforcement learning literature, and this is the representation learning literature. And to be honest, I believe a lot in representation. Half of the semester, I was coming to this class by doing the round. Only if one of you actually opened the other door, I was able to come here much faster. Do you see? Like, we really do not explore. We just, just follow around and so on. But maybe it's just because me, I'm not very much into exploration. I like, but yeah. Okay. So excellent ideas again about sensory input. And again, you are very lucky because these good ideas came out the last 1-2 years. All right. So we have seen this before. We took this low dimensional state and we trained a dynamics model, and you're going to implement this in your homework 4, correct? And here is what we're going to discuss today. Now, the input is videos. Okay. So how can we learn models from visual input? And 2 things to keep in mind. We have the same big decision to make, which, by the way, this big decision was very open and very, debatable and hot about 2-3 years ago. Now, the last 2 years, the decision is clear. Okay. And again, mu0 was a pioneering paper in that direction. Now, unfortunately, mu0 is not well written. So people don't even get it. So I have some slides from another paper that actually, very interestingly, don't cite, we say, we copy paste the method. No, it was tried to, it was written independently, but has very beautiful visuals, and I think you'll appreciate the ideas there. And by the way, that last paper we're going to present was actually the exam paper of last semester. So I gave them at exam time. Okay, so here are the two choices. Either you will predict the next image, you'll predict the future in pixel space, or you will jump to a latent space and you predict the future in a latent space. Okay? So in both cases, what we're looking for is a model that takes a state and action and spits out the next state. And that next state, I need to be able to fit it back into my model to predict the next state, and again, the next state, and so on. This is what we're looking for. And we're saying that there are 2 choices. One is the prediction to stay in pixel space. So you predict the pixels themselves, and then you fit them back. You predict again pixels and so on. Or you take your images, you jump to some latent space, like 1D vector, some 2D vectors, you don't care. Bunch of set of vectors is not a graph of vectors. And then you predict the next state, which you fit back. And you never worry about predicting pixels. Okay? Are the 2 choices clear? The first are called pixel prediction models, and the second is called latent dynamics models. Okay, latent dynamics, because you predict in the latent space. Okay, so I'll go back to ask you questions about which one would you prefer, except if somebody has a very strong opinion of why one should be better than the other. Yes?
Just inherently by abstracting away from the pixels allows for better generalization. You train over a bunch of different situations in the same latent space. And if you need to regenerate the pixels, it has to hold on to some of the less useful information that you may want an adjunctive bias to.
Great. So your colleague said the following. He said 2 things. He said, by jumping in a latent space, maybe I'll generalize better. And the second thing he said is, if you predict pixels, there are a lot of pixel information that has nothing to do with the task. For example, you want to predict whether I'm going to go left and right. I mean, the fact that there's my jacket doesn't depend, or the laptop and so on. So if you predict pixels, there's going to be a sky in the back, how the leaves are blowing, and so on, that are really, really relevant to your task, right? And there is a great paper, actually, Gabe had found that paper. The title of the paper is People Build Abstract Representations to Plan. We, to do look ahead, we really, really build very abstract, very succinct representations that are super, super task relevant. Okay. Now the generalization, I don't really agree, but that's another story. The reason we don't agree is because, you know, this guy, to jump to that latent space, there are some, parameters here. So if this guy looks different, then this guy also is going to fail. Let's say you trained only with a black background. If you just put the CNN to jump to the latent space, that CNN is going to go crazy if you give it green background. So you may need some extra inductive bias, but that's another story. Is that everybody agrees with our colleague that says, you know, pixel prediction will actually always squeeze the capacity and stress out the model to predict task irrelevant information? Yes?
I think if you don't have a good training set of going from like pixel to latent space to latent action, it might be better just have a complete end-to-end model depending on the task from pixels to action and not have like two separate models.
Right, but where are the separate models?
From like pixels to latent space and then latent space to action.
Oh, great. So now, very nice. So I think what your colleague said is that, oh, this sounds to me very awkward because it's not end-to-end, right? First, you need to jump to the latent space, which let's call this the representation model that takes you from image to latent. And then you need to learn the dynamics of that latent space. Let's call this a dynamics model, right? And how I'm going to train those two is super unclear. And in fact, we're going to go exactly to say why this is super unclear, right? And precisely because it's so difficult even to think about it, guys, just because I totally agree with your colleague, that's precisely why people started from the second, where you predict pixels, because here things are obvious. You just have a plain supervised learning problem and you know how to do. You just stack up frames, take an action, spit out the next frame, supervise with the 2 pixel error. It's just a regression. You're done. Do you see? That's why people put a lot of emphasis. It was crazy about 2 years ago. And even today, people are, you know, very obsessed about predicting the pixels of videos because it's just so easy and so conceptually simple. Okay. But I really like your colleague's comment because he's hinting towards like there are a lot of non-clear things of how to do things here, right? How to do things right there. And this is precisely what we'll visit. So let's jump directly to a very representative paper of the second category of models, which is also very fun. Yeah, so model learning from sensory input is an open problem. If you know LeCun's paper recently with a very long title, I think it's like a pathway to AI. He just mentions, you know, building world models as the open research problem. Okay, how do we endow, machines with the ability to understand the world and how the world behaves? This is exactly related to building models about the world. Okay, like how the monster of the Atari is going to move, when the monster is going to shoot, where is the strawberry is going to show up? Can I hide behind the tree? Do I fit in the cave and so on? Right. So this is also about learning world models from Atari. Correct? So, but let's start simple. And I show you here a very baseline architecture for predicting, you know, frames in Atari games. Okay, so here it is. This is the paper. I think it's 2017, action condition video prediction using deep nets in Atari games. And you see the very simple architecture of we take an image, we take one of how many actions in Atari, we take the one-hot encoding of that action, and we feed them into a model, and then we predict the next image, right? And how we're going to supervise this model? Yeah, you have an image, do that action, you get the next image, and you just trace supervised, like a regressor, right? Exactly. So given an image sequence, and an action predicts the pixels of the next frame, and then this is ready. Now you can take this prediction, feed it back as input, and predict further into the future. So let's see here. So this orange arrow shows that whatever you predict, you can feed it back and predict again, and so on and so forth. And by the way, this frame here that you feed, it doesn't need to be a single frame. You can take 4 frames, then you throw away the first, you stack the last, and continue. Yeah. So, all right. So, by the way, here is an interesting thing, and this all has to do with wiring of the network. You don't take an image and concatenate the action and feed it. What they did is they took an image, they went to some encoded latent features here. There, they concatenated the action and then predict. They really want the action to really be able to, you know, touch every visual feature. Okay, so you do this type of wirings. By the way, back then there were no transformers, So now you just put the action and the vision and you put the transformer and you're done. Okay. So you don't need to worry. But back then we really worried like, oh, in which layer shall we put that connection and so on. But now attention is all you need. So you just feed the inputs and you do well. By the way, there is a very good paper now that I mentioned transformers. Maybe we will look at it. Yeah. So here is the single problem that you need to worry when you care to predict pixels in videos. The single problem is that because you feed your model into your predictions early in training will be really bad. And then you're going to be feeding your network bad things. And then you'll ask it to predict the right things. And the network won't be able to converge. Okay, this is in general a problem when you train sequence models. So what do you think we should do? So because if you take the model and say, oh yeah, let me unroll it 10 times. So each time I'll predict and feed it back and predict the next and feed it back and predict the next. And here I'm going to have 10 losses, one for every frame that I need to be predicting. And the first frame is going to look awesome and the other 9 are going to look random pretty much because my weights in the beginning are random. It's going to be very difficult for the network to learn. What is a very simple trick that we do to stabilize training in this case? Okay, so basically whatever I'm saying here is that if you just predict given the right image to predict the next, and that's it, and then at test time you just unroll it, the network is going to be very surprised because instead of seeing ground truth images, it sees its own predictions. And then you may say, oh, but I'll train it a lot. Sure, you'll train it a lot, but still at some point there's going to be some deviation. And when the network sees that deviation, it cannot recover. All right, that's the problem. It's the same error accumulation that we saw in imitation learning, maybe. It's just that here we don't deploy anything in the world. We just feed predictions. So the solution, do you guys understand the problem?
So the same problem in model predictive control where we were only choosing one action and not a series of actions.
Yeah, so no, it's not exactly the same. This is just training. At model predictive control, it was, we've trained somehow the dynamics model and it was great, okay, but still there are errors, okay, still there are errors. Here is not that, okay, you're going to train a model, there's going to be errors, it's going to be actually super crap. You won't be able to use that model, okay? And the way we do it, guys, is very simple, is instead of just training using ground truth to predict the next frame, you also add more losses. What are those losses? First, with ground truth, I'll predict the next frame. Then, yes. Yeah, then I'll feed my prediction at training, right? And then predict the next, and I will have multiple losses coming from different amounts of using my own predictions further in the future. And the way to train, at least the way they trained, is first you predict the first frame. So here is whatever we just said. So you take the action and the observation and predict only the next observation. And we said that this is doomed. So what are we going to do instead? Instead, we're going to say, don't worry, I'll have multiple ones. Here is the ground truth observation. Here's the action. I'll predict observation. I will also feed this back as input my network and predict the next one. Here I know what is the right observation. So I'll put loss both here and here. Okay. And in the first step, I have ground truth. And here I have my own prediction fed. And guess what? You can just do more and more of those. Now feed those all three with another action to another and get all four and so on. This is precisely what this shows. This is a number of training examples. And essentially, you start with predicting, and then you feed it back and predict again, and feed it back and predict again. Okay? And when you train, first you're going to train with this, then you'll converge, then you'll train with 2 terms, then you'll converge, then with 3, then you'll converge. And these people said that they train with 100 unrolls at training time, like something incredible. But does this make sense to you? Okay, that's it. So we don't just train to predict the next, we feed it back and train exactly the same way that we will test the model. That's what this says. Okay? Okay. So let's see how things look like. So you see the prediction. Oh. The prediction is on the left and the ground truth is on the right. So what do you think about the prediction? Does it look good to you, or what is not perfect? What is missing? by the way, this step shows you the prediction into the future. You see the predictions into the future. So it's just predicting further and further in the future. So what is missing from the prediction compared to the ground truth? Yes. Which one? Yeah, the bullets, right? And it turns out that, so why do you think the bullets are missing? Why the bullets are missing and those red guys are not missing?
Small and transient.
They're very small and they're transient. And because they're small, they have a very small pixel error in comparison to the red monsters, right? Yeah, that's the problem. That here, when you do pixel error prediction, you weigh as much as your volume, okay, as many number of pixels that you occupy. Is that clear? And it turns out that bullets are super task relevant. So the last thing you want is to, forget the bullets. But that's what pixel prediction does. And here's another game. Again, I don't see bullets here. Yeah, so now you know the problem. All right, so small objects are missed, the bullets, and we tell why, because they induce a very tiny mean pixel prediction error, okay, despite the fact that they're super task relevant. Now I want to ask you, to make this network to be more task relevant, can you think of a very, very simple method to do that? Can we think of a very simple method to do that?
Does predicting residual helps? Like instead of predicting the next frame, I predict the difference between next frame and current frame.
Yeah, many people do that. Yes, this overall helps because of the tremendous amount of redundancy in temporal streams. Usually, we predict the deltas. You're absolutely right. Okay. Now, given if we have access to rewards in our trajectories, it always helps to also predict the reward signal. Like, okay. Now, the problem with the reward signal is what? In comparison to predicting the image. Why don't we just predict rewards and we're done? I mean, okay, this is for the second part of the lecture, but rewards are very sparse in time. Okay, so while images are there available to you, but also here is a paper, a follow-up paper that again is doing prediction in observation space, again predicts frames and feeds them back as input, okay, but also predicts the reward, okay? So as you predict the frame, you also can predict the reward, and if the reward is related to the bullet or to the explosion and so on, those things will be retained, hopefully, in your output image, to be able to predict the rewards not only of the next time step, but also of the subsequent time steps. So this is one obvious way to make your pixel predictor more task relevant, okay? So this paper is an important paper because it was the first one a model-based paper, and from that era where everybody was predicting in observation space to actually do better than a Pondel-free method. Let me show you. Okay, let me first of all tell you how it works. Sure. It works as follows. You train your dynamics model to predict the next observation and reward. Here it is. And then you sample from your dynamics model and collect simulation experience, okay, by enrolling and so on. And then you train PPO. By the way, the previous paper just showed that, look, I learned the model. It didn't use that model to train a policy. This is the paper that actually used the model to train a policy. Okay? All right. So they do the obvious things that we discussed from Wednesday's lecture. You first collect a bunch of data, you train a model, you sample the model to get synthetic experience, a tremendous amounts of synthetic experience, plus some real experience, and then you use your favorite model, free reinforcement learning methods that for them was PPO. Okay, now there is one tiny detail on the model that let's not go through right now because there are better ways that we're going to see how this is going to be encoded in later lectures. Their model is not deterministic. The previous model we just saw is deterministic. You just train good regression, there are no latent variables and so on. This one is not, okay? It has discrete latent variables in the model, but we will see Dreamer V2, which is another very state-of-the-art paper at Atari Games that actually uses those discrete latent variables. So you don't need, this is an optional reading for today. But I think it's an important paper because it's the first one that actually used the model-based reinforcement learning method in observation space to actually do better than model-free methods. And I'll show you what means to do better. So the model is stochastic and has discrete latent variables to handle multimodality because Atari is not a deterministic domain like Go. Is that clear? So we haven't discussed about this topic again, but we will touch it maybe next week on Monday. Yeah, so basically, yeah, so you also predict the rewards. At the same time, they decide to make the ball larger, which is super weird. They decided, okay, ball matters, let me enlarge it. And, you know, in this way, my model now pays some more attention and so on. So yeah. So these are all problems that happen when you put your dynamics in observation space, okay? In latent space, hopefully that latent feature will have a big chunk for the ball and a very tiny thing of saying, oh, you know, by the way, the background is brown. Okay. But here, PPO alone without the synthetic experience does this, and model-based does that. Oh, it says here is the number of frames required to reach human performance, and now you see the model-based technique requires much less amount of real experience. Real experience means in the simulator. Okay, so what is the takeaway so far? The takeaway is that people started model-based reinforcement learning by predicting in the sensory grounded agents that take videos as input by predicting the future in pixels, in pixel space, and feeding the predictions back as input. The problem with this type of prediction is that, as your colleague pointed out, pixels are not task relevant. And when you have a pixel image, you do not know the task, so you don't know how to assign different weights in different parts of the image. Oh, this is the bullet and it's important. Oh, this is, you know, the sky and it's really not important. You put the same loss in every pixel, all right? So essentially you have a loss that has nothing to do with what you're trying to do, which is do better in Atari games, all right? Learn to play Atari games. Okay, so we just saw one effort that tried to use this type of networks, this type of dynamics, to do better than a completely model-free method, and it succeeded because we showed that by having the model and sampling synthetic experience from it, you can reach human performance with much less actual experience. And this is precisely how we evaluate performance of reinforcement learning methods. Rewards versus amount of data that you use, okay? Amount of experience, amount of interactions. So let's go back to our picture. Let's see. Do we really need to be predicting pixels? Okay. And there was this paper that came out that's called the Predictron that said, no, we don't need to be predicting pixels. What if we just jump in a latent space and predict from there task relevant quantities? And then we'll see how we should be able to do that end to end. Now I'll show you some failed attempts of that, okay, before going to the real solution. So people said, okay, great. Let me not be predicting pixels. I'll put here, I'll take a bunch of frames. Then I'm going to jump into some latent space, okay, or some internal features of my network. Here is my action. And then I'll feed it into my dynamics model, all right? And I'll predict the next time step. And here is the next time step. And I will use an encoder again. And then I will take this loss, okay? So instead of taking the loss at pixel space, I take it at the latent space, the space of my encoder, the output space of my encoder, okay? And as you see, there are two subnetworks. The brown one, which let's call it the representation network that takes you from images to a latent space, and the gray one that actually, given that latent space, latent vector is trying, and an action, try to predict what will be the next latent vector. Okay, and now, and imagine that I supply this loss here. Okay, and you need this loss should be able to update both networks, the encoder and the dynamics. Well, okay, so this is there's no phi prime, by the way. This is just a theta and phi. So this is a typo. So my question for you guys is the following: is this can this be trained end to end with end to end back propagation? is this whole combination of networks differentiable? Yeah, I mean, I can help you. So here you have 4 frames, you put the CNN, you go to the top layer, you flatten it, you combine some action representation here, like one hot encoding or something, you feed them in MLP, you predict another vector, then you take that whatever encoder of the next frame, you encode it, right, into some flattened vector, and you put an L2 loss. Is this end-to-end differentiable? What do you think? Because you said that, oh, this is going to not be end-to-end.
It seems like you have an issue when you're trying to train both F and ZT plus 1.
ZT is not on, is nothing here. It's just the encoder. I think the reason I have 2 different Fs is because this encoder can take multiple frames, and this one can take only 1 frame.
No, I'm saying you don't know if you want to bring your F closer to the ZT plus 1, or if you want to bring your ZT plus 1 closer to the F.
So ZT is the feature activation, and F are parameters of a network. So you can never bring parameters close to activations. You only bring activations close to each other.
Sorry, excuse me. The predicted ZT versus the actual ZT. It seems unclear how you want to bring this closer.
But 1 second now. But this is actually the case in every metric learning. Both of them, they just need to be close to each other. And that's it. It doesn't need to who's going to go first close. Who cares? The parameters are going to be updated so that the only thing you care about is them to be close to one another.
Why can't they both just be 0 then? Always.
Under this cost function, correct?
Right.
Exactly. This is the problem here. The problem is there is nothing that prevents this of collapsing. Of course, it's end-to-end differentiable. Of course, I can backpropagate. I just wired together some differentiable functions, but there is a trivial solution. All right. And when we were predicting in pixel space, there was no trivial solution. Why? Because I have the actual pixels there that I need to predict. Okay. Is that clear? Now, of course, okay, so that's one problem. Now I want to ask you, can you find a baseline way to get this thing not to collapse and to actually do this to be useful? Yes. Yeah, how to force them not to be zeros? Yes. Yeah, you can use the contrastive task, but the problem is then that I'm not sure if you can feed back and unroll and go forward and so on. In fact, I had some contrastive prediction slides here, but I think they're just confusing because if you don't match with L2, then how you're supposed to, feed them back and predict again and so on, right? Because we're trying to unroll. I mean, let me just say, do you remember the trick we did in the previous paper? We predicted reward. So reward, unfortunately, is sparse in time. But if you ask your representation here to predicting, instead of just the future, also the reward, then they cannot collapse. Because in some frames, the reward will be 0, in some 100, in some minus 50. So for sure, they cannot all go to 0. Because, do you guys agree? You agree. So this is an obvious thing that you can do. Now, the problem with rewards in reinforcement learning is they're extremely sparse. That's the problem. So you would need immense amount of experience to get something useful coming out of here just by predicting the reward, correct? Do you agree? So I'll tell you some other solutions that people found, and we'll come back to that. Okay. But by the way, the solution will be, don't just predict the rewards, predict also actions and Q values. That's the solution. That's what mu0 does. That's what the paper we're going to see does, and so on. And all the rest is the same. So whatever I show here in this slide that, as correctly your colleague pointed out, this is not a correct optimization problem. Well, we'll add some extra losses and everything is going to work out. Okay? Great. All right. So let's see what other, so here's what people did. They said, okay, it collapses. So what I'm going to do, well, what if I take my latent features and put them into a decoder to be predicting pixels? Okay, so in this way, my latent space is visually grounded. Okay, for example, yes. So basically, you train an autoencoder to go from an image back to the same image. Then you take this as your encoded feature vector, and you add this remaining losses. That's it. So basically, we have exactly the same thing as before, but we also add on top of this an autoencoding objective. Yes.
Wouldn't the encoding not really be useful because we're trying to use it to get rewards, not to encode a picture.
Yeah.
It's not a great encoding.
I agree. Well, you can predict also your reward.
Yeah, you can, but it's not optimized for like the fact that the ball's location.
Exactly. So your colleague says the following. Then he says, I don't see how we did now much better than the previous paper. I mean, the previous paper had to predict in pixel space, and this is very stressful. And now we went to an image space, but now latent space, but now we are asked that latent space to again decode pixels. So how did we get over the previous problem? And you are absolutely right. That's precisely what people are saying. Like if you reconstruct images, then again, you're stressing out your latent space to predict task irrelevant quantities. That's the problem. This is precisely what we're trying to avoid, correct? Okay. Exactly. So this is not a good solution, but people tried it. Okay. Yeah. And yeah, so this is now the real solution. Yeah, I think I said everything I needed to say. So the question is, how can we learn a latent dynamics model without reconstructing pixels? That's the idea. All right. This consistency that we predict the future and then next image is encoded and we match on the encoded space. So we never need to remember all pixels back. That's the question. So the solution, guys, is going to be the following. We will be predicting task relevant quantities. That's it. Not just the rewards, because unfortunately rewards are sparse, but we're predicting actions and we're predicting Q values. Okay. And so let's see now a paper that actually puts this together. Yeah. I need to switch, unfortunately, but I think. Yes. So here is temporal difference learning for model predictive control, a very nicely written paper that combines the main idea is what we just said. We learn a dynamics model in a latent space that predicts task relevant quantities. They applied it both for learning the dynamics from low dimensional state, an alternative to PETs, as well as from images. Nothing. The only thing you need to change is your encoder, that the presentation network that takes you from whatever your input, raw input, which can be pixels or it can be, low dimensional states, to the latent space. They also have some 2-3 very good ideas that people use them. So that's why we're going to visit and see all these ideas together. So this is a required reading for today. Okay. Yeah. So we are at particular status 0, and we want to select actions and to maximize some certain reward. And we don't have access to the model of the environment, and we need to optimize this objective. And unfortunately, it is intractable. And what we're going to do? Well, we're going to do planning. And because we cannot plan to the infinite horizon, this is related to what your colleague asked earlier, this rollout that needs to end. He said, how we can have a rollout since we didn't play till the end of the game mentally? We would never be reaching the end of the game. We will always be planning till a horizon H or capital T, depending on what we want to call it. And then from there, we'll truncate. Okay, we'll truncate the trajectory. Is that clear? Okay. Okay, great. So the problem with models is that they compound error and that there is low horizon planning and it's very costly and so on. So here is one idea that I'm not sure this paper was the first to introduce, but I really want you to know about it. So here is the idea. When I compute a trajectory, okay, when I compute a trajectory, by the way, just to see, so clearly this is, I mean, for you, it's going to be very natural because we use Monte Carlo research. Monte Carlo research also unrolls trajectories in a more methodic way. We need to compute how good is that trajectory. Do you agree? We need to be doing, let's say, in PETs, for example, when we did the cross-entropy method, we were doing some search over actions by doing evolutionary search. We had Gaussian distributions for actions at every time step, and we were trying to find what are the right mu's and sigmas from where we're going to sample the actions for every time step so that our trajectories have high fitness scores. Do you agree? And do you remember how we computed the fitness scores of those trajectories? How we compute when a trajectory is good or not? Okay, so I'm sure you know that. Let me explain. There is nothing, how good is a trajectory depends on its return. What is the return? Sum of rewards, okay? So when I give you a trajectory and you need to compute the fitness, how good is that, right? What would you do? Yeah.
Run it on some.
No, because the whole point is that mentally you are unrolling those trajectories. You want to be, okay, let me try to think. Okay, so in Monte Carlo research, how did we decide when a trajectory was good or not? Did you remember what we did? We were going down. How did we evaluate, okay, how good is this trajectory? Yes.
Didn't we take the average of the results through each like node that we pass through and like save them?
Yeah, that is the how good is the trajectory. Well, that trajectory. Well, here's the thing. Because that is a Markov game, you know, if that trajectory lands in a particular leaf node, how good is the trajectory depends on how good is that leaf node. What is your chance of winning the game from that leaf node? Do you remember how we evaluated that? What is our estimate of how good was a leaf node? Yes? Okay. Let me try to think. So let's say I have a model that given a state and action tries to predict the next state, is trained to predict the next state and the reward. Okay. And now I sample actions. I just sample action. I want to do evolutionary search. I have, let's say, a planning horizon, 5 or 10, and I want to find those 5 or 10 actions that will give me the highest, sum of rewards, right? So what I'm going to do is I'm going to sample, I'm going to initialize my Gaussians at every time step, sample actions, okay, get bunch of trajectories, and compute their fitness scores. And the fitness scores in PETS was sum of rewards. The fitness scores in MCTS is the value of the leaf node. How good is the leaf node, right? I need an estimate of how good is that trajectory. And that estimate is not a real thing because everything runs in my head. You see, I'm not executing anything in the environment. This is just a mental search. Planning is just a mental search, right? So I have my model that tells me how good is the reward at every time step of that trajectory, correct? I sample actions. I feed them into my model. I get rewards per time step in the next states and so on, right? So going from sequence of actions, I feed them to my model and I get action, state, reward, action, state, reward, action, state, reward. Okay? Now, sum the rewards, and I tell you how good is that trajectory. And trajectories that are good, they're like, okay, let's sample, the Gaussians that gave rise to those actions. I want to move their mean of those temporal dependent Gaussians towards the actions that gave me highest fitness score trajectories. So this is precisely PETS. This is precisely what you're going to implement your homework for. Is that clear? Okay, so we'll see the same plan. Now, the problem is the following. If the horizon is long, if the task has a very long horizon to be completed, and the only thing you're doing is you enroll for 5 steps, and then you only look at the rewards on those 5 steps, then what happens after, right? You just discard it? Do you see what I mean? No, in Monte Carlo research, we have this value function. The value function, we take into account everything beyond that, right? Because if you remember, we trained that value function to tell us in this state what is my chance of winning the game. So what would be the corresponding of that value function here? Well, the same thing, value functions. Instead of value functions, we're going to be training Q functions. And let me show you exactly what I mean. Yeah, this is exactly what I mean. So the estimates will be this. The sum of rewards for all the intermediate steps plus the Q of the last step. Now we need the Q here because depends also what actions I take. So Q and V is exactly the same. It's just Q is also conditions on action. So basically, whatever happens after the end of my trajectory is modeled with that Q function. Do you see how important this is? Now I want to ask you, where were those terms in Go? Because in Go, we didn't consider those terms, right? We didn't consider instantaneous rewards. We only consider goodness of a leaf, yes. Yeah, there are no intermediate rewards in Go. That's what it is. In general environments, there are also going to be intermediate rewards. So along with the end of the leaf, essentially, this is the leaf state and action of a trajectory. You also need to take into account the intermediate rewards. Now, pets only had this guy. MCTS had only this guy represented with a value network, so don't get confused. And in this method, we're going to have the addition of those. And this is the most general form. Now, each time you do model predictive control, and you do mental search to search for an action, sequence of actions, this happens every day in your life, right? This is the most obvious thing somebody can do. You will have your dynamics model, and you will also be training a Q function, and you will have your Q function to help your planner. So if you see, guys, this is exactly an instantiation of AlphaGo 0, but with a learned model and without Monte Carlo research. So Monte Carlo is a very fancy optimization, and here we just roll trajectories, right? Monte Carlo search. No, there's no tree, but that's fine. It's still a look-ahead procedure. It's still an optimization and so on. So, okay, we'll continue on that super important paper on Wednesday, and we will also look at U0 and compare, and we'll also look at everything we've so far together and see, plus and minuses of each one and compare, and we'll put all the models that we've seen so far to see how everything fits in a very clear and unified story. So enjoy your Monday, and you enjoy your 3-chord treating, right? And then I'll see you on Wednesday.